this video, we're going to be talking about applying Newton's second law to inclined planes, which is a pretty common type of problem. So you can see here we have a ramp and there's a block sitting at the top of the ramp. And so in these problems, you'll also always get the angle that the ramp is making with the horizontal. So this angle theta tells you how high the ramp is sloped above the ground. So to get started, we can just draw all of the forces acting on this block. So we have gravity, which of course always points straight down. And then the normal force, it's not going to be pointing straight up because the normal force is always perpendicular to the surface that the object is on. So it's going to actually be slanted so that it's perpendicular to the ramp. And then we're going to also have friction, which is pointing the other way up the ramp to oppose the motion of the block down the ramp. So in order to analyze this situation, we're going to need to carefully choose a reference frame, in other words, a coordinate system. So usually when we just have an object moving on flat ground, then we just use a coordinate system with the x-axis being the ground and the y-axis pointing straight up. Now that's just the default, you don't even really think about it when you do a problem. But for inclined planes, it's most convenient to use a different coordinate system. So we're going to use a coordinate system where the x-axis is parallel to the ramp. So the x-axis is the ramp now, and so the y-axis is still perpendicular to the x-axis. So you can see that in a new coordinate system, friction is acting along the x-axis and the normal force is acting along the y-axis. So now what we have to do is deal with gravity, because gravity is not directly acting along either of the coordinate axes. So we can split up gravity into its x and y components in a new coordinate system. Here's the relation of the angle at the bottom of the ramp to the gravity vector. So you can see we can form this little triangle here. And then since this is a right triangle, the angles have to add up to 180 degrees. And since we have the right angle at the bottom left corner, then the other two angles must add up to 90. So that means the angle at the top is going to be 90 minus theta, where theta again is the angle that the ramp makes with the horizontal. But then we can make a new right triangle, with the components of the gravity vector. So you can see how where the right angle is, and of course again the other two angles in this yellow triangle must add up to 90 degrees. So that means the remaining angle is 90 minus 90 minus theta, or in other words, just theta. So you can see here that the angle in this gravity triangle turns out to be the same angle as the angle of the bottom of the ramp. So then we can use this angle to write out the x and y components of the gravity vector. The x component is going to be mg times sine of theta, because sine of theta is f of x over the hypotenuse, which is mg, or just the magnitude of the gravity vector. And then the y component is going to be mg times the cosine of theta. So now we have all of the forces on this object acting along one of the coordinate axes. So now we're ready to apply Newton's second law. So first we do it in the y direction to find out the normal force. So in the y direction, we have the normal force pointing up along the y-axis, and then the y component of gravity in the opposite direction. So we can solve for the normal force because we just found the y component of the gravity. So the normal force is exactly equal to the y component of gravity because no other forces are acting along the y-axis. So now in the x direction, we have the force x component of gravity pointing down the ramp and friction pointing up, resisting the motion. So we just found the x component of gravity, And now, since we found a normal force, we know that friction is the coefficient of friction mu times the normal force. So now we have both of these components, so we can write out the net force in the x direction. And then set that equal to the mass times the acceleration along the x-axis, which is just down the ramp. So I factored out the m and g from the expression of the net force, and then we can cancel out an m on both sides. So then we found the acceleration, and now we can integrate this to get the velocity down the ramp. So since all this is just a constant, we just add t at the end, and then have the plus c, the constant of integration. Solve for the c by plugging in time equals 0. If we set the time equals 0 to be when the block starts moving, so at time equals 0, the velocity is going to be the whatever initial velocity the block had. So c is equal to the initial velocity, because all the other stuff is cancels out when you set t equal to 0. So now finally we can solve for the position function along the x-axis by integrating again. So we get 1/2 of all this times t squared, add a t to the initial velocity, and then add another constant of integration, which turns out to be 0, because at t equals 0, then we're at the initial position, which we can define to be 0. So now we have a final expression for the position of this block sliding down the inclined plane. And we can check our answer with one special case. So let's say the theta is equal to 90 degrees, which means it's a straight up inclined plane. In other words, it's just going to be falling straight down, free fall. If theta is 90 degrees, then sine of theta is 1, cosine of theta is 0. So the equation simplifies to 1/2 gt squared plus the initial velocity times t, which, you know that equation from kinematics. It's just the equation of free fall. So in this video, we solved the equation for the motion of an object on an inclined plane with friction in the general case. General case meaning we didn't assign concrete values to the theta or the mass of the object or anything like that. So this equation is going to work for pretty much any situation on an inclined plane. But you should not just memorize this equation. The important part was how we got the equation. Figuring out a coordinate system and then separating the forces into the x and y components on the new x and y axes, and then applying Newton's second law.